Everyone, my name is Yifan, and I'm a second-year PhD student in UMich, and today I'm presenting our work, the CoNav Chair design of a shared control-based wheelchair for the built environment. We will begin with the background and challenge motivating this work, then describing the methodology, the hardware and software design, followed by our experiment setup and results, and both in simulation environment and real-world usability study, and conclude with some key takeaways and future directions. Let's begin with the background and challenge. According to WHO, more than 1/4 in the US live with some form of disability. Among those, mobility issue is the most significant barrier to independence in built environment. The manual control-based wheelchair rely entirely on user's input through interfaces like the joystick, brain signals, or eye tracking. Will this allow for direct control and it is much safe? They require skills, attentions, and physical disability and may not be accessible to everyone. Autonomous wheelchairs use LiDAR, cameras, and IMU to build maps and navigate without human input. They enhance accessibility, but often cannot adapt to any environment, which means it can struggle in dynamic environments. For example, we will proposing the safety issue, especially when navigating near people. This motivates a shared control-based approach, which both the user and the autonomous system collaborate. The robot will leverage the perception and planning, but still listen to human input, makes the navigation safer and more intuitive, especially in a predictable space. Let's talk about the design of the CoNav chair. Our hardware platform, the CoNav chair, is built on a powered wheelchair base and equipped with a LiDAR, a Z stereo camera, and a wheel encoder. This configuration supports robust sensing for indoor environment. The software stack integrates the user's input with autonomy. It includes a global planner informed by user's preference, a social area detection to respect pedestrian comfort zone, and a socially aware NPC local planner with dynamic barrier function that ensures the safe real-time motion around people and obstacles. To begin with, in a path planning pipeline, from A to B is usually planned as a straight path as optimal, but things will be different when considering the user's preference. So to take the user's preference into global planning pipeline, we use a 2D Gaussian-based user preference field, creating a cost valley around the user's preferred path waypoint. Since the path planning algorithm always plans the paths that yield the lowest cost, the path generated will be attracted to the user's preferred waypoint based on the cost map, while avoiding the obstacles. For the local planner, we proposed a socially aware NPC with a dynamic control barrier function, which takes the pedestrian social area and user's control into the local planning pipeline. One additional condition for the dynamic control barrier function is calculated in the NPC constraint, and the user's control is taken into consideration into the cost function. It will help the robot to avoid the obstacles and generate a safer and more effective path for the robot. Then let's talk about the experiment and the result. We used two simulation environments to test our framework. Open source with one side of full of obstacles to test our global planner, and a narrow corridor with obstacles to test our proposed local planner. And on the right side, it is our wheelchair detail twin model. We evaluated the global planner on path accuracy compared with the user design path and using the matrix like the error time plot. And we also evaluate the local planner using the matrix like the obstacle distance, the time and the trajectory smoothness under the static and dynamic conditions. Compared with the baseline A star, and our user preference field planner reduce the error over time by steering the path closer to user's intent. And from the plot from the right side, The proposed planner can generate a less risky path compared with the general A-star global planner. In static environments, from the figure, the shared control outperformed both manual control and fully autonomous NPC-based control. It leads to fewer collisions, smoother paths, and a shorter time, showing the benefit of incorporating users' input even when navigating through the tight space, such like the corridor. We selected three different scenarios: the crossing, aggressive passing, and distracted passing to test the most common dynamic situations in our daily life. In crossing experiment, we allow the robot to pass through 5 people, in which all people will be aware of each other's moving using the social NPC. From the result, the shared control demonstrated a smoother path and higher efficiency compared with other baseline. The aggressive passing experiment is that the people and robot will go to the opposite direction, where people won't aware the moving, which force the assistive wheelchair to react accordingly. With shared control, the users were able to slow down or reroute early, showcase a safer and smoother path. We also simulated cases where the pedestrians behaved erratically in distracted passing scenarios. So in these distracting scenarios, the shared control helped the robot to avoid sudden intrusions and change the direction accordingly. Our proposed method of the most efficient, safe, and smooth methods according to the different kind of metrics shown in the table. Besides the simulation experiment, we also recruited 21 participants and conducted a real-world experiment in a university building corridor. Each participant will try to navigate three different modes: manual control, autonomous control, and shared control. The study will aim to access the usability, the safety, and the satisfaction from people. We observed that in shared control, the user primarily takes control over when near the obstacles, indicating the trust in autonomy, but also a desire to assert control when necessary. The control frequency of the shared control is much smaller than manual control, indicating a lower mental requirement. Objectively, the shared control resulted in the lowest completion time, shortest path length, and collisions. The curvature variance was also lower, indicating a smoother trajectories. Those metrics suggest that the shared control strikes the best performance balance. Subjectively, the user rated shared control the highest in efficiency, safety, and ease of use, especially participants without prior experience using the joysticks. This confirms that the shared control enhanced both the performance and users' confidence. Goes to the conclusion. To conclude, the CoNav Chair demonstrates that the shared control significantly enhanced indoor navigation for people with disability. Looking forward, we plan to reduce the system latency and integrate alternative inputs like the voice and eye tracking to better support the user with limited ability. Our work is featured by the Text Explorer and Michigan Engineering News. A video demo is linked here. And thanks for your attention. We are happy to take any questions.